Hello students, welcome to Energy Conversion 2 class. We are doing with chapter 3, that is Synchronous Motor, and today's topic for discussion is different starting methods of synchronous motor. So, synchronous motors run at synchronous speed. Obviously, the synchronous speed of a motor depends upon the supply frequency and the number of poles in the motor. We can also say synchronous speed is given by Ns equals 120 into F by P, where F is the supply frequency and P is the number of poles. We can change the synchronous speed of a motor. How? By changing the supply frequency and the number of poles of that particular machine. But the motor would always run with this speed for a given supply and the number of poles. Again, the synchronous motors have lots of advantages, but being not self-starting, unlike three-phase induction motors, is a major disadvantage. We have already discussed, students, that the three-phase induction motor is a self-starting type of electric machine. But this synchronous motor is not a self-starting machine. Again, in synchronous motors, the stator has three-phase windings and is excited by three-phase supply, whereas the rotor is excited by DC supply. The three-phase windings provide rotating flux, whereas the DC supply provides the constant flux to the machine. The torque produced on the rotor is a pulsating one and non-unidirectional. Considering the frequency to be 50 Hz, from the above relation, we can see that the three-phase rotating flux rotates about 3000 revolutions in 1 minute, or we can say 50 revolutions in a single second, in 1 second. Now, at a particular instant, rotor and stator poles might be of the same polarity, that is north-north or south-south, causing the repulsive force. As we know, like poles repel each other. A repulsive force on the rotor, and the very next second it will be north-south, causing an attractive force. But due to the inertia of the rotor, it is unable to rotate in any direction due to attractive or repulsive forces and remain in standstill condition. Due to this, the motor cannot start on its own. The rotor of the synchronous motor has to be brought to synchronous speed by using external means. First, starting of a synchronous motor using an induction motor. This is the first method of starting. So, we need to bring the rotor of the synchronous motor to synchronous speed before we switch on the motor. For that reason, we directly couple a small induction motor, it is otherwise known as pony motor, with the synchronous motor. Note here that the number of poles of the induction motor should be less than the synchronous motor, else it will never be able to achieve the synchronous speed of the synchronous motor. Again, this is because an induction motor always has a speed less than the synchronous speed, and for it to become equal to the synchronous speed of the synchronous motor, its own speed has to be increased. After the rotor of the synchronous motor is brought to synchronous speed, we switch on the DC supply to the rotor. After that, we simply decouple the induction motor from the motor shaft. So, for the starting purpose only, here an extra small induction motor is used, and this induction motor is known as pony motor. Now, coming to second method of starting. starting a synchronous motor using a DC machine. It is similar to the above method, that is using induction motor, with a slight difference in the two. A DC machine is coupled to the synchronous motor. The DC machine works like a DC motor initially and brings the synchronous motor to synchronous speed. Once it achieves the synchronous speed, the DC machine works like a DC generator and supplies DC to the rotor of the synchronous motor. This method offers easy starting and better efficiency than the earlier methods. Now, the third method of starting a synchronous motor using damper windings. In this method, the motor is first started as an induction motor and then starts running as a synchronous motor after achieving synchronous speed. For this, damper windings are used. Damper windings are additional windings consisting of copper bars placed in the slots in the pole faces. The ends of the copper bars are short-circuited. These windings behave as the rotor of an induction motor. When three-phase power is supplied to the motor starts running as an induction motor at a speed below the synchronous speed. After some time, the DC supply is given to the motor and the motor starts. The motor gets pulled into synchronism after some instant of time and starts running as a synchronous motor. When the motor reaches synchronous speed, there is no induced EMF in the damper windings anymore, and hence they don't have any effect now on the working of the motor. This is the most commonly used technique for starting synchronous motors. Now, the fourth method, starting a synchronous motor using slip ring induction motor. Here we connect one external rheostat in series with the rotor. The motor is first started as a slip ring induction motor. The resistance is gradually cut off as the motor gains speed. When it achieves near synchronous speed, DC excitation is given to the rotor and it is pulled into synchronism. Then it starts rotating as a synchronous motor. So now we will discuss another important concept in synchronous motor, that is hunting. We come across the term hunting when we study about three-phase synchronous motor operations. The word hunting is used because after the sudden application of load, the rotor has to search or hunt for its new equilibrium position. That phenomenon is referred to as hunting in a synchronous motor. Now let us know what is the condition of equilibrium in case of synchronous motor. A steady state operation of synchronous motor is a condition of equilibrium in which the electromagnetic torque is equal and opposite to the load torque. In steady state, the rotor runs at synchronous speed, thereby maintaining a constant value of torque angle, that is delta. If there is a sudden change in the load torque, the equilibrium is distributed and there is resulting torque which changes the speed of the motor. So, here we can say this is the settling time hunting period without damper winding. Here we have taken time, here we have taken load angle. So, at this point of load angle, this is the new equilibrium position and this is the settling time due to damper winding. This whole time is the hunting period without damper winding. So, these unwanted oscillations occurring in the synchronous motor waveform are known as hunting. Unloaded synchronous machine has 0° load angle. On increasing the shaft load gradually, load angle will increase. Let us consider that load P1 is applied suddenly to unloaded machine shaft. So, machine will slow down momentarily. Also, load angle delta increases from 0° and become delta 1. During the first swing, electrical power developed is equal to mechanical load P1. Equilibrium is not established, so rotor swings further. Now, the load angle exceeds delta 1 and becomes delta 2. Now, electrical power generated is greater than the previous one. The rotor attains synchronous speed, but it does not stay in synchronous speed and it will continue to increase beyond synchronous speed. The machine will go beyond the synchronous speed. As a result of rotor acceleration above synchronous speed, the load angle decreases. So, once again no equilibrium attained. Thus, rotor swings or oscillate about new equilibrium position. This phenomenon is known as hunting or phase swinging. Hunting occurs not only in synchronous motors but also in the synchronous generators, often abrupt change in load. So, overall we can conclude that when there is an abruption or there is a change in load, there is a sudden change in load. For that instant, for that particular time, there will be unwanted oscillations. The machine will try to achieve the new equilibrium point. That condition is known as hunting. Now, what are the causes of hunting in synchronous motor? The different causes for hunting in an synchronous motor can be sudden change in the load, sudden change in the field current, a load containing harmonic torque, or any fault in the supply system. So, now we will discuss what are the effects of hunting in synchronous motor. The effects of hunting on the synchronous motor will be it may lead to loss of synchronism. It produces mechanical stresses in the rotor shaft. It increases machine losses and cause temperature rise. It causes greater surges in current and power flow. It also increases possibility of resonance. Now, how to reduce the hunting? Two techniques should be used to reduce hunting. Number 1, by using damper winding. It consists of a low electrical resistance copper or aluminum brush embedded in slots of pole faces in salient pole machine. Damper windings damp out the hunting, the unwanted oscillations by producing torque opposite to slip of the rotor. The magnitude of damping torque is always proportional to the slip speed. And the second method for reducing the hunting is use of flywheels. The prime mover is provided with a large and heavy flywheel. This increases the inertia of prime mover and helps in maintaining the rotor speed constant. Thank you.